Hello, this is Dr. Flight. It's good to have you join us for a quick discussion or review on regression. So regression is probably something that you've been exposed to, you've done before, you've worked with probably since high school. So what we'll talk about today is just a brief overview of regression and applying it in SPSS. But the things that you know about regression are things that are kind of been around for a long time. So we do regression for predictive purposes. We want to predict events that will happen in the future. We also want to show, very importantly, the relationship between variables. And that's really what we want to do when we think about marketing. We look at an outcome, and that would be our dependent variable, the Y variable in a regression model. And that outcome could be sales, it could be profit or some type of an income. It could be foot traffic into the store. It could be your churn rate, how many people buy who come into the store, in other words. It could be any number of different metrics that we want to measure, we want to keep track of. And so we have all these outcomes, and what we want to know is what influences those outcomes. And so those are our independent variables, or the X's, that are in the regression formula or model. So we want to predict outcomes, and we want to understand what makes an outcome happen. So prediction and this idea of relationship between variables is everything that we're focused on when we do this. So regression analysis then is a predictive analysis where we use multiple variables. We theoretically think, we form a theoretical model that says we think and we have hypotheses that these predictive variables will in fact predict and influence the variables that are our outcomes. Okay, so we have these independent variables then, and we have dependent variables. Again, the dependent variable is the Y variable. It's usually on the left-hand side of the equation. It's the variable that depends on the other variables, which are independent variables. Independent variables are sometimes, think of them as controls or variables that we don't have any influence on. We think of them as the ones that are going to influence the dependent variable. Okay, so simply said, we have two different types of regression. We have what's called bivariate regression, and then we have multivariate regression. So you're probably familiar with both. Bivariate regression is your simple slope of a line type of a curve. So we have just two variables when we do a bivariate regression. So this is going to be your typical, again, it's your linear slope line where we have y, which is the dependent variable, which is equal to a, and that's a constant. It's the point where the slope crosses the y-intercept, and then plus beta, and then an x variable. So x and y are our two variables. A will be something that is estimated when we do the regression. It'll be the constant term. And then B will be the coefficient that we associate with X. Again, B is also something that we estimate when we run the regression. Okay, B would be the slope of the line. So if you look at a simple slope formula, that's what it is. When we look at it in a graph, this is what it looks like. So again, this is 8th grade high school type of stats. We don't really do a lot of bivariate regressions. One of the things you can do is do a simple correlation between the two variables, the x and the y, and that R, that correlation, more or less tells you what that relationship is going to be like. So if you want to do a predictive model, then go ahead and do a regression, get your A, and get your B, and then put it into the formula to estimate what Y would be at any given points of X. But again, this is kind of one of these where we don't do a lot of them in practice because we want probably more sophisticated models, if you will. If you're going to predict a Y variable, you're probably going to have more than one X. That's basically at the end of the day. So that leads us to sort of a multivariate regression type of a thing. If we're going to use SPSS, it's a pretty simple process. We go up to the top of the SPSS banner ribbon where there's the Analyze button. We hit that, we press on that, and a drop-down menu will be offered. We do regression and then linear regression. Now on the regression panel, when the drop-down comes, there's going to be a bunch of different drop-downs. There's going to be a lot of different models that you can do. But there should be just a simple regression or a linear model that you can check there. And a dialog box will open up, and you're going to be offered to put in independent variables and dependent variables. Now remember, these variables need to be scale. They need to be metric. Ideally, in the theoretical perfect world, those variables also need to be normally distributed. Now, regression tends to be very robust, especially if you have a very large sample size. So you can overcome some of the issues that are associated with data if it's not normally distributed. So that's not like a hard, fast rule. In other words, if you have scale data and it's not perfectly normally distributed, it's not the end of the world. You're still probably going to run regression and go from there. Okay, so X and Y's, they need to be, again, normally distributed. They need to be scale variables. Okay, the general conceptual model, again, it's going to be look like we just had. In this particular case, we have a dependent variable called intention to buy. So that's the outcome. That's what like the consumer's plan or expectation that they will buy, their plan to buy, and cost. I don't know how cost is defined here. I don't know how the scale works. If it's a price, it'd probably be inversely related, but we're not sure exactly how the scale is. This is just kind of an example where we have a cost that's associated with a purchase and then the intention to buy. Okay, so you run the model, click OK once you have your variables inside the dialog box, and you get a result. And this is what the result's going to look like. There's going to be a couple things to look at. When you get down the screen a little bit, you'll have a box that gives the estimations for A and B. Remember, A is the constant, so A would be where the slope of the line crosses the x-intercept if you were going to graph this. And then the B is the actual slope, the rise or the run, the B. And so if we look at this, look at the variable, the results, 0.297, that's the B. A we don't really have a test for A. We don't look for significance for A, but for B we certainly do, and that's what we want to do. So so the thing to look at is how big is that beta? It's 0.297, so that's a pretty good size, okay? And we'll kind of look at significance in a second. A minor point, or a point that is a nuance that you need to know eventually, is if you're going to do a prediction model, then you use the unstandardized beta, so the 0.297. If we had multiple variables and we wanted to compare the relative strength of each variable, each B or each X, excuse me, then we would look at the standardized coefficients, okay? But if you want to interpret the b in a regression in a predictive model, then the 0.297 is what you do. So again, the measurement model, if I want to predict intention to buy and I just have cost, then this is the model that you do. This is the formula. And so this is a predictive model. So again, remember the idea of regression is kind of twofold. One is we want to do predictions. Number two, we want to show relationships between variables. We want to understand what those relationships are. So those are two really important things that we want to get out of a regression analysis. In this case, we're looking at that 0.297, seeing that it's big. So we have a strong relationship. It's positive. So, because it's not negative, so it's a positive relationship. So we have direction. So I have strength and direction. And then we put that into our formula. And then anytime we have cost, we can estimate what intention to buy will be based on what we have here. Okay, the other thing that we're going to look at is at the other side of this box, we have the t statistic. Okay, and the t statistic is when you do a t-test, what you're doing is you're measuring whether the distance of the number from 0 is significant or not. And so we have a t-test. The t-value for cost is 3.9. And what that's looking at is that the 2.97, is that significantly different from 0? That's the question that we're at. That's the test. Is 2.97 significantly different from 0? And again, for this, we always, the general rule is to use 0.05 as your significant cutoff. So anything below 0.05 in the significance box, we'll say is significant. It is. So we look at this and we look at the significant box there, and it's 0.000. So we know that this cost has a significant influence on intention to buy, right? That's what that says. And it's because the 0.297 is significantly different from 0, right? That's what we're actually measuring when we look at that. Okay, so that's what we need to look at. We need to understand that when we do the model. And again, this is bivariate regression, so we only have two things going on. We need to extend it to have more than 2 x variables. So if we have more than 2 x variables, it means we have multiple regression, and it could look something a little bit more involved like this. So we still have our dependent variable, the y, on the left-hand side. We still have a, which is a constant, okay? And we don't really have anything to do with a. What we care about are the betas that are associated with each of the x variables. So in the last example, we just had one x, and it was cost, and we had one beta. Now we're going to have the option of multiple x's and multiple associated betas with those. Okay, so this is kind of what we look at as we look at a multiple regression model. Now there's a couple more issues associated with this type of modeling, and the thing to know, I guess, in short, is the biggest challenge, I guess, is when we produce these models, sometimes the x's are related to each other. And when they're related to each other, we call, and it's severe enough, we call that multi-collinearity. So and there are a few other things that you want to be kind of aware of and be cognizant of. Again, the x's need to be normally distributed. So that's something that we need to make sure that's there. Again, if they're not, it's not the end of the world. The other thing, though, I'd caution everybody against is the collinearity among x variables. That will produce results that are not entirely, you can't really, I don't know what the right word is. You can't always believe what you're seeing, I guess, if there's a lot of multicollinearity. You got to filter through that. So in a previous video, I said that whenever I do a data analysis, the first thing I do is do a correlation matrix. So in this case, what you want to do is with your y variable and with your x variables, run a correlation matrix, do a correlation, and if any of the x variables are highly correlated, then consider dropping one of them. Okay, try running the model a few times, but try dropping one of those correlated variables. Okay, and when I say correlated, I mean like if it's correlated at 6 or 7 or higher. If the R is 0.6 or 0.7 or higher, I would take out one of those x's, run the model, rerun the model with the other x, and just kind of see how it goes. Okay, so in other words, correlation among x's is called multicollinearity, and what it'll end up doing is obscuring which variables are actually predicting y. And so that's kind of, as you kind of get into it, that's kind of one of the challenges. Okay, so now we're going to do the SPSS calculation of a multivariate analysis. And in this case, again, we have the top ribbon of SPSS where we have the analyze, drop-down box, regression, and then linear. You can play around with different types of regressions if you want, but this is what we're doing. We're doing a linear regression. This time, though, in the dialog box, we're going to have an opportunity to put in more variables because we have more variables. So we have a dependent variable, which will be intention to buy again. And then we'll have a variety of different independent variables. And I have the variables here, and I don't necessarily need to know what they are right now. If this was my research, if I was collecting the data, I would know directly what cost, attend, and version are. But in this case, I'm just putting the model together as an example. Okay, so here's the measurement model, or the conceptual model, where we have IB, which is intention to buy, which is equal to the constant A. And then we're going to add to that a weight or a beta associated with cost, and then another second beta for attend, and a third beta for version. Now remember, when we estimate this model, A, B1, B2, and B3 will be the things that are estimated. The A is the constant, B1, B2, B3 will be the betas, their coefficients, and those are the things we're going to look for and look at specifically to see if they are significant, so statistically significant, and see what size they are and see how they behave in relation to explaining the variance in intention to buy. Okay, so we run the model, and as we run it, we'll have a results box that pops up here. And as we look at this result, the results of this this data, we're going to, again, look at the beta, the size of the betas, and then we'll also look at significance. And so as we look at those, we have, again, the B1, B2, B3. B1 is 2.81, so decimal to 0.281. B2, the beta associated with attend, is really, 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 really small. So that's a -5. So that's a scientific notation, right? So imagine 5 places to the left. So decimal 4 zeros, 2829. That's a really, really small number. That's very close to 0. So you could say that that's a really, has almost no influence on intention to buy, right? Just because it's so small. Version is a negative, so it has a negative relationship, but it's pretty big in an absolute value, so 0.376. It's bigger than the beta for cost, again, in an absolute value. The minus sign just means direction, right? So it's negatively related. So the bigger version gets, the smaller IB gets, because they're inversely related. If we move on over and look at the significance levels, anything below 0.05 is significant. So again, we're looking at the betas here. So cost 0.001, version 0.065. Okay, so that's interesting. It's still it's above 0.05, so you could question whether that's significant or not. And then 0.545 for attend, it's no way that's significant. Okay, now a little bit about predictions and a little bit about significance. 0.05 is the benchmark, and you need to establish that ahead of time. And then anything that violates that, you don't move forward, or you say is insignificant. So if we did a hypothesis test or we did a t-test, we would drop the version because it's above 0.05. The curious thing, though, is that its beta is pretty big, bigger than cost, yet it's less significant than cost. And the reason why this is going to happen, and the reason why this is an issue, is there is very, very likely a lot of collinearity between cost and version. That'd be my guess, because this is an unusual behavior, okay? The reality is, if I was a researcher, I'd run it again with either cost or version dropped out, and I'd play around. I'd run 3 or 4 versions of the model and see what worked and what worked best. Okay, you know, so that would be kind of the step forward as we went forward. Again, my guess is that cost and version are both explaining the same variance to some degree of IB. And so that's why we see some weird significance levels that don't really correspond with those betas so much. Okay, so takeaway here, though, is that if this was the model, we know that attend really is not a player, if you will, in predicting this. If we were going to do a measurement model, again, if we're going to use this as a predictive model to predict by, then we would have cost in there. We'd have that minus 376 for the version, and we could keep the attend in there, but it really doesn't add anything to the value because it's such a very, 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 very small number. It doesn't hurt to keep it in there, except that you typically want to be keep models as small as possible if you can. So so that's kind of where we are with that. Okay. All right, moving on. Model fit. So once we run the model, once we look at the different strengths of relationships and directions of relationships, one of the things we can do is come away with, okay, is this a good model or not? Should I add more variables? Should I drop variables? Should I move this forward? Is this a good predictive model? And there's going to be a couple things that we can look at. First and foremost is what's called the F statistic. The F statistic will be in a box above, you know, kind of at the beginning of this. It's in the ANOVA table of the report. The F statistic tells us if any parts of the model do a good job in predicting the dependent variable. Thing is, though, it doesn't tell us what parts of the model. Okay, so it doesn't really dig in and tell us which variables are important. It just tells us something is important. So it's a global representation. In practice, the F statistic really doesn't tell us much, if anything, useful. So people will always say, oh, look at the F statistic. My F statistic's significant. It's not hard to have a significant F statistic. So again, in practice, it's not something that we look at to a great degree. What we do look at, though, is the R. So we have R and then R squared. So the R is the correlation coefficient. R squared is the coefficient of determination. And so R squared helps take into account multicollinearity, and it indicates how much variance the independent variables actually explain in the dependent variable. Okay, so it's the explanatory value of the dependent variables in relation to the into the independent variables in relation to the dependent variable. This can be really small, and that's not good. We want robust and well-sized R-squareds in these models. So in our last equation, in our last one, we have an R and then the R squared and then the adjusted R squared. Okay, so we look at the R squared, total variance explained in the independent variables. Once we start looking at the adjusted R squared, the big thing here is to see how much, the degree to which that changes. If you see a big drop, then it's kind of problematic, and it really suggests there's a lot of multicollinearity. So that's where that drop goes. So we go from 208 to 186. Now, 208 is not particularly good to begin with. If I'm looking at R squareds, a 208 isn't going to be fantastic. It's acceptable, and again, we have significance in the model. The model F statistic is significant, and then the betas are significant. So R squared doesn't tell really the whole picture. The dropping down to 186, though, is probably not desirable. It's probably not something that we would be excited about in terms of reporting and the predictability. So this means a couple things. It would mean that, one, there's probably a good amount of shared variance, and we already know there's probably is anyways. So I need to look at my variables, and I need to look at the correlation again in them. More importantly, though, if I'm trying to predict cost, what it probably means is that there are a whole lot of other variables out there that I haven't considered and I haven't put into my model. So in other words, this model, while it's not wrong, it's probably not sufficient. Okay, so we have three variables. One doesn't really do anything to the model itself. We probably need, I don't know, a half a dozen more variables. We probably need more variables that relate to cost, or intention to buy, excuse me, to fully understand it and better predict it. Okay, so the model's not bad with what it has. It operates and functions correctly, but it's not very powerful, right? So that's kind of where you go with a multivariate type of a regression. It's the interpreting, it's not the doing, it's not the getting the betas. It's really kind of understanding how good the model is and whether it's going to be useful to you. And whether you need to find more variables or eliminate variables where there's a lot of shared variance. Okay, so this comes from practice. At the end of the day, though, as we kind of look at cleaning up the model and figuring out how it's all going to be, how it's all going to go down. Number one, assess the statistical significance of the overall regression. So yes, look at the F statistic, and if it's not significant, then you're in big trouble because it's easy for that to be significant. Number two, evaluate the R2s, R squared, sorry, the R squared and the adjusted R square, and see what it looks like. If it's above 2, 3, 4, then you're probably in good shape for soft sciences. I know for hard sciences and in different types of research, you want it much higher. But in social sciences, it doesn't need to be off the charts high. Okay, number three, examine the regression coefficients and their t-statistics to see which ones are statistically significant. So look at the betas, look at the size of the betas, and see the t-statistics and see if those are significant or not in your model, right? So that's kind of what you do. And at the end of the day, we need to assess these betas. We need to look to see if they are positive, the way we expect them to be, or negative, so the direction. We also want to look at the relative strength they are, and how powerful they are in predicting the Y variable. Consider dropping betas if there's shared variance, if there's a lot of correlation among the X's, or if they're not significant, if the t-value is too small. Also consider adding variables if your R squared is too small and you don't feel like your predictive power is going to be strong enough for the for what you're trying to find. Okay. All right, so that's regression. My suggestion is that you get a data set and you just run regressions and practice them and practice interpreting them. Okay, so anyways, have a great afternoon, great day, great morning whenever you're listening to this, and reach out to me if you have any questions. Thank you.